Section 5.2, perpendicular bisectors. We're going to learn about the perpendicular bisector theorem and its converse, and we are going to use those to find some missing information. So first of all, perpendicular bisector is a segment ray or line that is perpendicular to a segment at its midpoint. So if you look at CP right here, it is a perpendicular bisector of segment AB. And again, it's perpendicular at its midpoint, so that means it cuts AB into two equal pieces. So, equidistant is a word that we use in math, and it kind of, again, sounds like equi, which is equal, and distant, which is distance. So a point is equidistant from two figures if the point is the same distance from each figure. So that's just kind of a word that comes up in some of definitions and so forth. So equidistant is the same basically as equal distance. So we have two theorems dealing with perpendicular bisectors. Well, a theorem and its converse, I guess. So the perpendicular bisector theorem says, in a plane, if a point is on the perpendicular bisector of a segment, then is equidistant from the endpoints of the segment. So I can see that CP is perpendicular at the midpoint of AB. So CP is the perpendicular bisector of AB. And if that's the case, we can see that point C is on the perpendicular bisector. So point C right here is on the perpendicular bisector. So what that means is that CA right here will be equal distance or equidistant to each of the endpoints of the segment AB. So that means that CA is equal to CB. The length or the distance between points C and A is the same as the length or distance between points C and B. So if you know a point is on the perpendicular bisector, then it's equidistance or the same distance to endpoints of that segment it's bisecting. That's what the perpendicular bisector theorem says. The converse is the opposite. Remember, it switches the hypothesis and conclusion around. So now the converse says, in a plane, if a point is shown to be equidistant from the endpoints of the segment, then that point is on the perpendicular bisector. So in this case, we can see that if DA right here is equal to DB, which it's showing that as a marking, then we know that point D right here, then lies on that perpendicular bisector. So that means it's going to lie on that perpendicular bisector. Now, the perpendicular bisector doesn't have to be always extended. But if we extend that line, you can see that it would continue in each direction. And that point D would be on it. So then what that tells you is that it's on the perpendicular bisector. So it gives you the fact that there's this perpendicular and that it's splitting the segment into two pieces. So now let's go through a few examples and see if we can use that information. It says find the length of CD. So if you notice here, we are finding, they want us to find the length of CD. So that's this piece right here, and in the second example, it's this piece right here. They want us to find the length of CD. Well, in the first example here, we can see that BD is the perpendicular bisector. And we can show that simply because it's marked that way, but we can also see that these two are marked equidistant, so we know that that is on the perpendicular bisector, so these two pieces will be equal to each other. So all we have to do is set 2x plus 4 equal to 4x. And when we subtract 2x and move things around, we get x equals 2. So now to find CD, we simply substitute 2 in for x, and so we get CD is equal to 8 units. In the second example, we can see that D right here is on the perpendicular bisector. So that means it is equidistant to the endpoints here, so it makes those two the same length. So then 8x minus 4 is equal to 3x plus 1. Again, moving things around, we would end up to get 5x equals 5 and nx equals 1. So then again, to find CD, we simply plug in our value of 1. And so CD then is equal to 4 units. So that's really just using the perpendicular bisector theorem and its converse. So let's get a little more involved problem where we have to look maybe a little closer at a few things. So it says in the diagram, EH is the perpendicular bisector of DF. So here is DF right here. And it tells us that EH is the perpendicular bisector. So what that means is not only that perpendicular marking that they already put in for us, but it means that these two pieces will be congruent to each other. So that's what I know so far. I also know, then they just want me to find all of these things, EF, FG, and FH. So what does that tell us? Well, it tells us that those two pieces are equal. But notice I don't have the other side there. But what you can do is you can see that point E right here is on that perpendicular bisector. So it's going to be equidistant to the endpoints of the segment it's bisecting. So it makes these two equal to each other. So now I can set up 7x plus 9 equal to 9x minus 1. And subtracting and moving around, again, combining the x's on one side and the numbers on the other, I get 2x equals 10 or x equals 5. So how does that help me? Well, one of the things I'm supposed to find is FG, EF, which I can find EF now. So now I can find EF, which is that segment right here, by simply plugging in my value of x. So I have 7 times 5 plus 9, and so EF is equal to 44 units. All right, so if you extend that perpendicular bisector, okay, you also see that G, point G, right here, is also on that perpendicular bisector. And so these two are also going to be congruent to each other. They're actually already marked that way. So that means that 7y plus 8 is equal to 10y minus 4. And then subtracting, putting the y's on one side, the numbers on the other, that gives me 12 is equal to 3y, and so y equals 4. And so again, one of the segments I'm supposed to find here is FG, and now that I know y right here, I can plug it in. So I have 7 times 4 plus 8, so FG is equal to 36 units. Now, I can finally find FH because I know both x and y. So I can find FH by plugging in the x and the y. I know FH is equal to 3x plus 4y, and now that I know x is 5 and y is 4, I can substitute those in, and that gives me 15 plus 16, or 31 units. Okay, so let's just stop here again, and let's just see if we can prove this. Let's not even do a formal proof. Let's just talk about it. It says, given that CD right here is the perpendicular, a bisector of AB. So what that means is that it's perpendicular and it's bisecting. So those two are the same. We also know that CD right here is reflexive in each of those triangles. And what I'm supposed to prove is those two triangles, ACD, is congruent, that the triangles are congruent, so BCD. So the two halves of the larger triangle that we just split. Well, can I prove a triangle congruent with a side, an angle, and a side? Side, angle, side. Yes, I can. So the triangles will be congruent by side, angle, side. And the reason you have that is you have, by definition of perpendicular bisector, AD will be congruent. I put a B there instead of a D. So AD will be congruent to BD, by definition perpendicular bisector, and we have the angle ADC and angle BDC are both 90 degrees, so congruent by definition of perpendicular bisector as well. And CD is congruent to CD by reflexive. So the triangles are congruent. So let's talk about something called concurrency next. So when three or more lines, rays, segments intersect in the same point, they are called concurrent lines. And where they meet is called the point of concurrency. So there happens to be a theorem about the concurrency of perpendicular bisectors. P right here is the point of concurrency, because what you have here, what you have here is you have this segment right here. I wanted to actually use a different color here. So you have BP and you have AP and you have CP right there, and where those three lines intersect is called that point of concurrency, P. And if those are all perpendicular bisectors of a triangle, they intersect at a point that is equidistant from the vertices. So what that means is that it is equidistant to each of those vertices. So I'm going to go back here and just highlight this point again. This P is the point of concurrency. And actually, they didn't, if I should have come back here and started at this piece right here, if PD right here, so that is one perpendicular bisector, and PE is another perpendicular bisector. I'll color code this a little bit better here. And PF is a perpendicular bisector. Then they're meeting at that point of concurrency right there, P. And that point of concurrency is equidistant from each vertice right here of the triangle. So that means that these three segments from that point of concurrency to the vertice Each vertice is the same distance. And that's what this piece says right here. That the distance between points A and P and B, and P and C will all be equal. And remember, if they talk about this point of concurrency being the perpendicular bisector's point of concurrency, that also tells you that all of these other, when it says it's the perpendicular bisector, then it means that this piece and this piece are congruent and these are perpendicular. Remember, that's by definition of what that perpendicular bisector means. So keep all of those things in mind. Now that point of concurrency actually has not only special significance, but it has a name. And that point of concurrency is in the point of concurrency of perpendicular bisectors is called a circumcenter. Called the circumcenter. All right, so let's first use that idea, that concurrency of perpendicular bisectors theorem, to solve this, find some missing information. Okay, so in the diagram, the perpendicular bisectors of M and P meet at point O. So this right here is the point of concurrency of the perpendicular bisectors. And the perpendicular bisectors are the dashed lines. So then what that point concurrency theorem tells you is that from that point of concurrency to each of these vertices is equidistant. So this segment right here is congruent to this segment, which is congruent to this segment. Because those dashed lines, for example, like this one right here, what that tells you then is that it's perpendicular and bisecting it. So remember that. So now let's see what we can find. I just kind of tried to review some of those ideas. So now the first thing I want us to find is MO. So MO is this distance from here to here. Well, it's the same as from ON. So it is going to be 26.8 units. Now they want us to find PR. So PR is this distance right here. And again, because this is a perpendicular bisector right here, that makes this perpendicular and bisecting it. So that makes PR the same as RN. So that would make it 26 units. So how about MN? So MN is this whole segment. And so if this half MQ is 20, so is QN. So that is 40 units. All right, what about SP? So SP is this piece right here. And again, that SO is the perpendicular bisector. So it makes those two pieces the same, and so it makes it 22 units. QN is, we've already marked it because of the other work we did. And then finally MP is this whole segment right here, which would just be 44. All right, we have one more thing to talk about. And just when we talk about that circumcenter, remember the point of concurrency of three perpendicular bisectors of a triangle is called the circumcenter. And that circumcenter is equidistant from the three vertices. We already talked about that. So that can actually occur inside the triangle. And most commonly, okay, it could be inside the triangle. But if you have a right triangle, that point of concurrency will be on the circle. And if you have an obtuse triangle, that point of concurrency is outside the triangle. And again, if it is an acute triangle, it's inside the triangle. And that's just something to notice, especially if you're constructing the circumcenter. We already know how to do a perpendicular bisector construction, so if you do it on all three sides of your triangle, you will actually be able to find that circumcenter. And remember, the big important point here is that that circumcenter right here is equidistant from the three vertices. And here's one like really important example that can, why do we care about this stuff? Well, there's a lot of applications in business and in city planning. For example, it says in construction, a restaurant chain is planning to build a distribution center that is convenient to its three restaurants. The diagram shows the location of the restaurants, and if you take the location of each of these restaurants and draw lines between them, you get a triangle. So where would be the point that would be equidistant? Well, you would find the perpendicular bisectors of each side and that point of concurrency called the circumcenter. So in the diagram, how could you find a point that is equidistant from each location? Is you would find the circumcenter. And that's where you would construct your distribution center. So if I just sketch in, here's one perpendicular bisector, here's another perpendicular bisector, and here's a third. I'm just sketching these right now. It says make a sketch. This is where then that they should build that distribution center. Would be right here. And they do that a lot, like if they're doing fire stations and they want to put a new fire station in that's equidistant to three great big neighborhoods, that's another application of where this might be used. And that is the end of